Hi guys, welcome to section 7.4. We're looking at the normal approximation to the binomial probability distribution. I'm using my phone, so hopefully this isn't too shaky for you guys. But this is the worksheet that I handed out in class. Section 7.3 is on the first page, and section 7.4 starts right here. And then let's just kind of review some things because we're going to be using the normal approximation, we're going to be using the normal curve to approximate binomial probability distributions. So since we're going back to binomial distributions, let's remind ourselves what the mean of our binomial distribution is, and that is n times p, and the standard deviation is n times p times 1 minus p, where again n is the amount of trials, p is the probability of success, and then 1 minus p is the probability of failure. And then more importantly, the criteria to determine if our binomial random variable is approximately normally distributed, we saw in chapter 6, this was np times 1 minus p greater than or equal to 10. Okay, so if our binomial random variable is approximately normally distributed, what we're going to do is we're going to use a normal curve to approximate probabilities. Now this was useful for back in the day before graphing calculators. It was much easier to just come in and use the tables you can find in the back of your book for the normal curves to approximate binomials. I would argue that now that we have calculators to help us with binomial probabilities, we don't need this method as much, but it's still nice to know where the theory comes from. Okay, so I drew in our normal curve. This is a binomial distribution. It's a binomial probability histogram. And we see that we have this nice normal curve that we can use to approximate it. So let's see what this is going to look like. Let's see how this theory is going to work. So this is binomial, or the probability that x is equal to 9. This is on our binomial curve. And we're going to approximate it using our normal curve. So if we use our normal curve, so let's look at x is equal to 9. Now we know probability is area. So we would be looking at the area of this rectangle, like this. And so underneath the normal curve, if we wanted to approximate this area using the normal curve, we would look at the area under the normal curve from this point to this point. So this interval 8.5 to 9.5. So if we wanted to use the normal curve, we would have to look at the area under the normal curve from 8.5 to 9.5. And that would give us the area of the rectangle, or approximate area of the rectangle. Definitely we would be overshooting in this case. And there you go. So that's how we would approximate it using the normal curve. We would look at the area from 8.5 and 9.5. Let's look at more examples using 9. So for instance, let's say we wanted to look at the binomial underneath the binomial distribution, the probability that x is greater than or equal to 9. So that would be all these bars on the histogram. This one and this one, this, and this. Okay. So again, if we didn't have our calculator with us, that would be very difficult. So back in the day, what they did is they came in and said, well, let's approximate this with the normal curve. And then we can use our charts in the back of the book, and that would be much easier. But if we're using our normal curve, again, we're approximating using the normal curve, it would be all of these rectangles. And the rectangle is included at the 9. The 9 rectangle is also included. But notice our rectangle at 9, it actually starts at the halfway point between 8 and 9, so that's 8.5. So if we wanted to look at the probability that x was greater than or equal to 9 using our normal curve, we'd actually have to start at 8.5. Let me rewrite that. So it'd actually be probability that x is greater than or equal to 8.5 using our normal approximation. All right, and similar argument if x is less than or equal to 9. If x is less than or equal to 9, we'd be looking at the rectangles less than or equal to 9. So all of these rectangles, 9, 8, 7, 6, 5, 4, 3, etc., etc. But if we're using the normal curve, underneath the normal curve, our rectangle starts at 9.5. So we'd be using the normal curve for x less than or equal to 9.5. So using the normal curve, again, all the probabilities in purple are for the normal curve. We'd have to look at x less than or equal to 9.5. All right, and finally, for the probabilities, x less than 8. So again, that's on the binomial distribution. So if x is less than 8, it's always a little tricky. That means less than or equal to 7. So we can just remind ourselves, since the binomial probability, it's less than or equal to 7 on the binomial distribution. And that's approximated by the normal curve, but we have to go to the beginning of the rectangle, which starts at 7.5. So x less than or equal to 7.5. Okay, so when we're using our normal curve to approximate binomial distributions, we have to add 0.5 either to the left or right, depending on the situation. So let's look at some examples, or one example. So we have this situation again. 35% of all car-owning households have 3 or more cars. In a random sample of 400 car-owning households, approximate the probability that fewer than 150 have 3 or more cars. Okay, so we've calculated some of these before. Since we're using the normal approximation, we have to figure out our NP, our mean, since we're using the normal approximation, and we'd have to figure out our sigma sub x. All right. And again, it tells us that we're going to approximate the probability. So we're going to approximate the probability using the normal curve. That's why we're finding the mean and the standard deviation. And we already determined that this was 140 from a previous lecture, and this was the square root of 91. Okay, so if we want to approximate the probability that fewer than 150 have 3 or more cars, again, a good first step is always to write out what we're trying to find. Fewer than 150, but that's the same as less than or equal to 149. So if we want to approximate that using our normal curve, our rectangle, we can draw a little picture. Our rectangle, we'll draw it off to the side. Let's say this is our 149 rectangle. And we're going less than or equal to. So less than or equal to that 149. So if we're using our normal curve to approximate it, so again, probability is area, underneath the normal curve, we're actually starting at 149.5. So we can write x less than or equal to 149.5 under the normal curve. Okay, so now we can calculate this probability using normal CDF, because it's the area underneath the normal curve. Probability is area. All right, we have upper bound, or excuse me, we have our lower bound, we have our upper bound, we have our mean, and we have our standard deviation. Can't draw this anymore. Okay, and then we'll go to our handy calculator to help us figure this out. So normal CDF, second var is the distribution. It's the second one. We don't use normal PDF in this class, normal CDF. Upper bound, or I'm sorry, lower bound is -1 second e to the 99. Comma, our upper bound, 149.5. Our mean, which we found in a previous lecture, and the standard deviation. Oops. Okay, so the probability that fewer than 150 have 3 or more cars is approximately 84%. So there you go. And like I said back in the day when we didn't have calculators and we had all the charts in the back, this was much easier than calculating all these by hand. We can actually see how well the approximation is. So we can, for instance, check with binomial CDF. If we want to check with the binomial CDF, again, it's the cumulative. So our parameters would be n, p, and less than or equal to 149. And so let's see how well our approximation is, or how good our approximation is. So again, we're going to go to second vars on our calculator. All the way down. Our parameters are n, p, and less than or equal to 149. All right, so not that bad of an approximation. So we see this is what we had at first, and this is what we have now. So that's pretty cool. We have a pretty good approximation. I want to note, before I say goodbye, that in this previous example, we did this particular example in another lecture, and it was determined that this quantity NP times 1 minus p was already greater than or equal to 10, which meant that it was approximately bell-shaped. So that's the only reason why we can use this theory, is because we have that NP times 1 minus p is greater than or equal to 10, which means it's approximately bell-shaped, which means we can use the normal curve to estimate. All right, so that's it. Feel free to have a go at the rest. You have this one other example you guys can try out, and you have a whole back page as well.